Thank you very much for coming. This is the ME 429, which is propulsion system preliminary design. And for this particular presentation, we have a sponsored project by Pyramid Space, and it is the design of a liquid rocket engine. I'm not gonna steal their thunder for the presentation. I want to also thank the panel for joining us, and if you would, please just introduce yourself and maybe say just a little bit about
what we do.
What
Right. So my name is Connor Warren. I currently work for a company out in Mojave, and that's what I've done for the most part is mechanical engineering, CAD work, that kind of stuff, I guess, and been there for only about 6 months.
Tom Steinman, I'm an adjunct professor at Embry-Riddle. Been doing that since 2011. Prior to that, I worked at Pratt & Whitney and Honeywell for 42 years developing materials for aircraft engines.
Mike Fabian, I've been here since 2009 as a faculty member, previous Air Force, jet engine, and rockets.
Daniel Danley, first semester here, mechanical. Prior to coming here, worked for about 2.5 years in engineering consulting in the power propulsion phase of the chemical industry.
Michael Howitt, I graduated just a few months ago, also working out in Mojave, California area. Right now I'm working on thermal batteries and testing them for safety.
Alright, well, good morning ladies and gentlemen. My name is Jenna Humble and I am the team lead for Strava Designs. My teammates are Robert Ockenplatz, Marcus Bever, Eric Brown, and Chad Reinhardt, and this is our Phase 4 presentation. I'll start off by going over our project overview and requirements, and then we'll go into detail on our overall design, and then the specific designs of our combustion chamber geometry, our cooling system, our igniters and manifolding, our igniter, the test stand, and then we'll finish with our conclusions and recommendations. So I'll start us off with our project overview and requirements. As Dr. Haven mentioned earlier, we are sponsored by Pyramid Space. They are currently working on the design of a 1 metric ton liquid rocket engine for use as a second stage to orbit, as well as a lower atmospheric booster. We have been given $5,000 to implement both our system and the system of our related team, AL-not-LE, who is designing the gimbal for this engine. We have been tasked with the design of the thrust chamber assembly, or the TCA. We originally defined this as the combustion chamber and the associated interfacing. However, due to difficulties with receiving the injectors and igniter system, we have expanded our scope to include the design of the injectors and manifolding system as well as the igniter. In addition to designing the flight thrust chamber assembly, we are also designing a ground test engine, or GTE. This will be a version of the thrust chamber assembly that has made modifications for lower lead time and lower cost components. We will be making the ground test engine for the injectors and manifolding as well as the igniter, as opposed to the full thrust chamber assembly as previously scoped. We have also designed a test stand for this engine. We have capability for water flow testing, as well as we have maintained the capability for on-fire testing. The main project requirements are as follows. This must be a pump-fed engine, which means we have 1 electric pump for the fuel and 1 electric pump for the oxidizer. We are using LOX, liquid oxygen, and LNG, liquid natural gas, as our propellants, and as I mentioned earlier, this is a 2,200-pound thrust engine. We are required to be able to sustain a 400-second burn at 80% of our max thrust, and we are required to be able to throttle down to 20% of our max thrust. We also have a requirement for in-flight reignition, and we must be able to reuse this engine for multiple flights. This time I'll pass it over to Marcus Bever for our design overview.
Thank you, Jenna. Good morning. My name is Marcus Bever, and I'll start with an overview of our thrust chamber assembly, or TCA. So off to the right, or off to the left rather, we see our igniter system. This interfaces with the injector assembly while also providing hot gases directly into the combustion chamber. Now, to the right of that, we have our injector assembly, which is responsible for distributing the combustion gases within the chamber. it also provides an aspect of structural stability to the entire TCA. It is currently designed with a number of bolt flanges to facilitate testing. However, were a flight engine to be developed, these would likely be converted to brazed joints. We then have our combustion chamber, which has been extended to include a truncated parabolic nozzle, as will be discussed later on. For the operation, the liquid oxygen is fed from the pump directly into the dome manifold as part of the injector plate. This propellant then enters the combustion chamber. The liquid natural gas, however, is routed down to the lower fuel ring manifold, as seen in the far right bottom corner. This fuel then travels back up to the combustion chamber walls in the regenerative cooling system toward the injector plate. It then also enters the combustion chamber. We designed this TCA to operate at a mixed ratio of 3.2 parts oxidizer to 1 part fuel. Also driven by our propellant combustion characteristics is our combined propellant mass flow rate of 7.8 pounds mass per second. A chamber pressure of 1,000 psi was chosen in support of our throttleability requirement. This was one of our driving design decisions very early on. A preliminary model of our TCA predicts a mass of 20.0 pounds. Our TCA fits within a cylindrical size envelope of length 14.7 inches with a diameter of 8 inches. This will be useful for integration of the engine onto various applications. I will now continue on with the discussion of the various components that make up our combustion chamber. Specifically, I'll be focusing on aspects of our design to the right of the throat, which sits at just under 7 inches from the injector plate. First off, we have our TCA nozzle extension, using a truncated parabolic nozzle. This was developed in response to the requirement that our TCA be able to interface with interchangeable bell nozzles to support a variety of applications. As such, it was decided to position this seam downstream of the throat, as this not only had a lower temperature and pressure, but it also would have minimal impact to the flow of the combustion gases, as they would have already been accelerated to Mach 1 at the throat, would then be in the expansion phase. A length of 4.4 inches was chosen. A bell nozzle contour was developed through use of rocket propulsion analysis software, also used to develop the details of our combustion chamber. And it also provides support for a sealing channel in conjunction with the surrounding components. Moving on to our lower ring fuel manifold, which encompasses the truncated bell nozzle. This has been designed with a 0.57-inch diameter, as this allowed for tangential flow, or as this allowed the pipe to sit tangentially with the surrounding components. An eighth of an inch that pipe was chosen, and the fuel enters tangentially to support the cooling system. The inner contour has been designed to fit securely with the parabolic shape of the nozzle. Next, off to the right, we have our nozzle attachment plate. This serves the purpose of not only providing a physical attachment to the nozzle, but also serves to direct some of the flow into the regenerative cooling walls. Looking at the design more closely, we have 8 equally spaced holes that surround the circumference of the plate, being an 1/8 of an inch thick. A 1/8 inch fillet radius extends upwards, again to support the flow of the regenerative cooling fuel. The inner surface has once again been designed to fit snugly with the parabolic nozzle. And finally, it also provides support for a seal with the anticipation of an attached nozzle assembly. So looking at these components as an assembly that form the lower regions of our regenerative cooling system, is it expected that each of these components would be braced together, as we will not have the opportunity to manufacture these parts for testing. The fuel entering the lower fuel ring manifold is directly beneath the outer cooling wall shown in turquoise. An 1/8 of an inch gap was used here as a way to equalize the pressure distribution around the entire nozzle. However, a more in-depth fluid dynamic analysis will need to be undertaken in order to add credibility to this design and to refine it. The fuel then travels upwards, again, toward the injector plate once it enters the regenerative cooling system. With that, I'll be passing it off to Robert Auchincloss to discuss more details on the regenerative cooling assembly.
Thank you, Marcus. As said before, my name is Robert Auchincloss. I'll be going over chamber cooling. So our team opted to go with regenerative cooling design, which is very commonly used nowadays in liquid rocket engines due to its effectiveness in cooling down the combustion chamber. Regenerative cooling essentially works by piping in a coolant through a manifold at the end of the chamber due to the fact that the coolant flow opposes the hot gas flow inside the chamber. The coolant then travels through a channel or a passage along the length of the entire chamber, cooling down the combustion chamber. At that point, the coolant then enters the injector assembly, where it is then passed into the chamber and ignited to create the hot gas flow. The heat flux of the hot gas flow is absorbed through the chamber wall into the cryogenic cooling fluid. Our team had two major design considerations when deciding which regenerative cooling system to use: tubular wall design and coaxial shell. A tubular wall design is essentially a series of tubes that is shaped to the contour of the thrust chamber and then radially banded together to essentially create the combustion chamber itself. It is very commonly used in modern liquid rocket engines. However, it can be difficult to manufacture if you don't have the proper equipment. On the other side of things, a coaxial shell is essentially a design where you have a uniform thickness of a cooling channel that runs the length of the entire combustion chamber. This is less commonly used on larger liquid rocket engines, however, is much simpler to design and easier to model, and for these reasons, it was chosen for our rocket. A coolant comparison had to be performed between the two cryogenic fluids that we had available in our system: liquid oxygen and liquid natural gas. For liquid oxygen, there's a larger amount of it available compared to the amount of fuel due to our chosen oxidized fill ratio. However, it has poor thermophysical properties, meaning that it will become unstable and unpredictable at lower temperatures, meaning it is very useless as a fuel. On the other side of things, liquid natural gas, we have much less available to use. However, the LNG has much superior thermophysical properties, meaning it makes a superior coolant in our system. Also, it is very common nowadays in liquid rocket engines to use the fuel over the oxidizer to cool down the engine. A regenerative cooling analysis had to be performed in order to derive the initial chamber wall thickness and thickness of the channel through which the coolant will run. Initially, the chamber was subdivided into multiple sections, where the initial section, the pressure and temperature of the coolant was taken from the pump, and each respective section following was taken so that the exit temperature and pressure from the previous section became the initial temperature pressure of the following section. Using this analysis, we were able to march through the entire length of the combustion chamber, eventually ending up with the final temperature and pressure of the coolant as it enters the injector. From this, we were able to derive not only the chamber shell thickness, but also the diameter of the cooling passage, which the coolant will pass around the combustion chamber. Our current design features a coaxial shell, as was mentioned before. The chamber wall was determined to be 1/16 of an inch thick, with the coolant channel thickness being 0.34 inches, and the outer shell being 1/4 of an inch to maintain mostly the pressures that will be present inside the system. This is our current design of the cooling system. You have a cooling manifold where the cooling will enter from the pump along the end of the combustion chamber, will then be fed into this cooling passage here. It is attached to the outer shell, which is mainly there to maintain the pressures as well as create the actual cooling channel itself. The inner shell will then be suspended within the outer shell via a series of supports that will allow the structure to remain structurally intact. For the construction of the actual combustion chamber itself, the initial combustion chamber will be made in one single piece, where then 64 1/4-inch supports will be brazed on to the actual combustion chamber itself. Brazing is a process where a filler metal is used to melt two separate pieces of metal together in an oven. At that point in time, the outer shell will be manufactured in two separate parts and then brazed on in two separate sessions. For material consideration, we opted to go with Haynes 214 and Inconel alloy, mainly due to its strong thermal conductive properties, as well as the fact that it is resistant to oxidation, corrosion, and coking. Coking is essentially a buildup of hydrocarbons, which can cause restriction in our flow, which may cause eventual damage to our engine. I will now pass it off to Jenna Hummel for the injector assembly design.
Thank you, Robert. Again, my name is Jenna Hummel, and I will be going over the design we have come up with for our injectors and manifolding system. The purpose of the injectors is to introduce the propellants into the combustion chamber in a metered and steady manner. In order to do this, we have selected the unlike impinging doublet as our primary injector element. An unlike impinging doublet has one stream of fuel and one stream of oxidizer intersecting slightly down the combustion chamber, causing direct mixing. We chose the unlike impinging doublet as it is one of the most common used in industry and has been proven to be very dependable. It also provides direct and reasonably uniform mixing across the combustion chamber, which is optimal for efficient combustion. The one problem with this method is that it does create local mixture ratio variations around the injector elements themselves. Thus, it cannot be used next to the combustion chamber wall, as it would cause streaking on the wall, which will cause structural damage. In order to counteract this, we also opted to go with film shower head coolants, which are ports that direct the propellant directly down the combustion chamber itself. These will provide a uniform mixture ratio around the combustion chamber wall and also provide modest wall cooling. In order to determine what propellant to use in the shower head elements, we did two different analyses of the full injector plate, one with oxidizer as the shower head propellant and one with fuel. When determining which of these situations was more optimal for our engine, we looked at three main goals. We wanted to have the largest minimum required diameter. This will enable us to manufacture it more consistently, having consistent properties between the different injector elements, which will help with combustion stability. We also wanted to get as close to the maximum mixing efficiency diameter ratio as possible. Because we have an oxidizer to fuel ratio of 3.2, and we were designing for a specific pressure drop in the injectors, we were not able to actually reach the MME diameter ratio. However, we wanted to get as close as possible with our design. We were also designing to have as consistent flow properties going through these injector elements as possible, so that the results in the combustion chamber would be predictable. In all three of these categories, the oxidizer analysis was more optimal, as it had a larger diameter of 0.067 inches. It was also only 45% off from our MME diameter ratio, as opposed to 115 with the fuel. The oxidizer also proved to be more consistent with the flow properties, as the fuel would have to go through the regenerative cooling station, and during throttling, the propellant properties going into the combustion chamber would vary. The image you can see on your screen is the injector arrangement that we have determined. We have gone with 14 doublets arranged in two concentric rings of 7. We also have 7 oxidizer shower heads in a ring around the perimeter of our injector plate. Both the fuel and the oxidizer ports are at 0.067 inches in diameter. We have also designed both of these for an approximate pressure drop of 300 psi. This is 30% of our combustion chamber pressure and is on the higher range of this ratio. We did so to allow us to draw back the mass flow during throttling and still maintain combustion stability. We opted for a 60-degree overall impingement angle. We chose this because having a greater angle than 60 degrees, we run the risk of having backsplash of the propellant onto the injector plate, which can cause damage. Having an angle less than 60 degrees, the length of the streams before impingement gets much longer, and we run the risk of having the streams go unstable before reaching impingement, which means that we would not have the spray pattern that we expect. Within that 60 degrees, we selected the individual impingement angles to balance the momentum of the streams. As you can see on the screen, we have significantly different velocities entering our chamber, and the densities of the propellant are also significantly different. It is most optimal to have the propellant stream after impingement be axial along the combustion chamber. Therefore, we have gone with a 35-degree impingement for the fuel and a 25-degree impingement for the oxidizer. This results in less than 1 degree of difference between the propellant stream after impingement and the vertical axis. In order to get the propellant to the injectors themselves, we have to come up with a manifolding system, including a zoned oxidizer dome, an upper fuel ring manifold, and a platelet mounting system. This system has been designed to be modular for our purposes, as we can switch out any component in here during testing with minimal effort. This is because we have chosen to bolt our system together around the perimeter of our manifolding. However, for the flight engine, these will be brazed together, and those bolt holes will be used for the gimbal mounting system. Yeah, zoned oxidizer dome has been designed primarily with throttleability in mind. By having it zoned, we are able to turn off the oxidizer to the inner ring of doublets entirely. This allows us to drop our mass flow rate through the entire engine without dropping our mass flow rate through the individual injectors, which helps with our combustion stability. We have conservatively estimated that we are able to throttle down to 45% of our max thrust. This does not meet our 20% throttling requirement. However, we have decided that it would not be possible for us to reach that 20% without testing, as the combustion instabilities down under the 45% throttle range are unpredictable and are often coupled with the feed system, which we do not have at this point. We also designed this system to have large volumes in which we can have propellant diffusion. This lowers the velocity of our propellant in the manifolding and increases the similarity of the static pressure across each of the ports for our injectors, which creates uniform pressures in our actual injectors. This was the primary component that we redesigned for the ground test engine. The flight manifold can be seen on the left, where the ground test is on the right. They have the same internal structure, however, the outside machining has been simplified so that we have a much lower lead time and cost component. The upper fuel ring manifold has been designed to maintain our low velocities and our radial flow, as we are simply porting the propellant from the regenerative cooling system into the injector plate itself instead of collecting it elsewhere. This provides consistent flow to all of our injectors and will help with combustion stability. The two images on the screen now are the front and back of our passage plate. The purpose of the passage plate is to take the propellants from the two manifolds and connect them with the injectors themselves. Both oxidizer zones have been ported essentially directly from the manifold to the injectors themselves, though it should be noted that oxidizer zone 2 feeds not only the oxidizer portion of the outer ring of doublets, but also the shower heads. The fuel is slightly different as it enters the passage radially. It is also converged in passages so that we can maintain as much static pressure between the outer ring of doublets as the inner ring of doublets, as after the mass flow is taken out for the outer ring of doublets, we will have a significant pressure drop. We have opted to go with 6061 T6 aluminum for all components in our ground test engine, as we will not be hot firing this engine. However, in the flight model, we have decided on Haynes 214 for the injector plate due to its optimal oxidizing, corrosion, and coating resistance. It also has optimal high temperature properties, and it has little difference with the thermal expansion coefficient with our combustion chamber, which helps with sealing between the combustion chamber and the injector plate. This time I will hand it off to Chad Reinhardt for the igniter design.
Thank you, Jenna. As she said, my name is Chad Reinhardt, and I will be covering our igniter design. We elected to go with an augmented spark igniter system. This system is highly reliable in its ignition sequence, as well as supports engine restarts. The importance here is that it allows us to meet our in-flight restart requirement for the overall design. Additionally, an augmented spark system is reusable for multiple flights and has high durability. This also helps us meet the requirement of having a reusable engine, which is not as is becoming more common in the field today. The way an augmented spark igniter works is there is a small chamber separate from the main combustion chamber, in which propellants are initially fed. Once in the small chamber, they are ignited using a spark plug. This ignition creates a flame that then is propagated into the main combustion chamber. At this point, propellant is then fed into the main chamber, where it can be ignited by the igniter and then achieve full combustion. Once combustion is achieved, the igniter can either be left on during the full duration of a burn, or simply turned off, depending on the circumstances needed. While we did have many design influences for our igniter design, the primary one is a very common design used in industry. It uses liquid bipropellants for combustion, and in which it imports the oxidizer through a like-on-like impinging doublet located at the top of the igniter, and the fuel is ported in through a port in the side of the chamber. Additionally, this design utilizes a throatless converging nozzle for the exit geometry. This differs from the more typical converging diverging design that you see in most rock membranes. So on the right, you can see our igniter design, or a cross-section view of it. It will be using the same LOX and LNG that the TCA uses, except it will be receiving the propellants before the TCA. This means that the fuel will not have to first pass through the regenerative cooling system before reaching the igniter. This is beneficial in helping improve our ignition times. Additionally, we designed with a 20% pressure drop from between the feed pressure and the chamber pressure of the igniter. This was done as it would help to ensure that we had a higher operating pressure in the igniter compared to the 30% pressure drop for the main chamber. The reasoning for wanting a higher chamber pressure is to ensure that the combustion gases of the igniter continue to flow outwards and into the chamber, and you do not get any backflow going into the igniter. We did choose to keep the throatless nozzle design. This is because the throatless nozzle creates a wide dispersion angle of the combusted gases going into the chamber. This allows them to spread out more over the injector face and improve our ignition times. Similarly to the TCA, the igniter implements a platelet routing system. This involves a manifold as well as an injector plate located above the chamber. These three components can either be bolted or braced together as needed. And the benefit to this design is that it is modular. So as designs change or as the parts possibly become damaged, they can be easily replaced without having to remanufacture the entire igniter. For the LOX manifold's purpose is to receive the liquid oxygen from the feed system and then distribute it to each of the injectors. It is designed symmetric so that it will have even distribution of propellant to both injectors. And it was designed with a low flow velocity of 10 feet per second. This helps to reduce undesirable flow characteristics such as eddies that would keep us from having uniform flow to each injector. Finally, there is a threaded hole in the center in which a spark plug would be mounted to begin the ignition. For propellant injection, the LOX, as I said, will be entering through an injector plate that is fed by a manifold. This injector plate consists of a like-on-like impinging doublet that has a 60-degree impingement angle. Similar to the TCA injectors, this 60-degree impingement angle was found to be beneficial in that it reduces the amount of splashback of propellant onto the spark plug. Additionally, the injectors of this plate are approximately 70% smaller than the ones in the TCA. This is due to the significantly lower mass flow rates present in the igniter. This plate also has a threaded hole to allow the spark plug to extend into the igniter combustion chamber. The natural gas will be entering through a port in the side of the chamber. This port is placed such that it is tangential to the chamber wall, the inner chamber wall. This allows for the fuel to swirl around the inside of the chamber as it enters. And the combination of the swirling fuel as well as the impinging oxidizer creates a hot core combustion. This means that the highest combustion temperatures are present in the center of the chamber, allowing for cooler temperatures to be present on the chamber walls. This helps to improve the durability as well as the lifetime of the igniter. The igniter chamber is designed such that it will thread into the center of the TCA manifold. The reasoning for this is that it allows for the igniter to be easily removed for either replacement or repair, and additionally allows for it to help secure the plates of the TCA together during testing. The chamber inner geometry of the chamber was designed as if it were another liquid rocket engine. This means that we took into account the propellant characteristics, such as the oxidizer fuel ratio of 3.2. This was chosen to be the same as the TCA. The operating pressure, which was chosen as 1300 psi, and the exit conditions, which in this case had to be equal to that of the main chamber operating conditions. This helps us to ensure that even while the engine is running, the igniter can function properly as needed. For the material selection of the igniter, we did opt to go for 6061 T6 aluminum. The main benefit is that one of the benefits is that it's easy to machine and has low cost. The amount of material needed for a single igniter costs right around $10, so it allows us to reiterate as much as needed during testing. Additionally, aluminum has beneficial heat transfer properties for our uses and remains ductile at low temperatures. This ductility is important as the fuel propellants coming into the igniter will still be cryogenic. And then finally, the igniter will be made of the same material as the TCA manifold. This is important as it allows us to not have the issues due to dissimilar metals, such as increased corrosion rates and different thermal expansion coefficients. And I'll pass it off to Eric Brown for our testing and design and device.
Thank you, Chad. As Chad said, my name is Eric Brown, and I will now be covering the test stand design and analysis. The purpose of the test stand is to provide a stable platform for the mounting of the gimbaling system, our ground test engine, and any test equipment, any test equipment necessary during testing. The test stand requirements were initially developed for our initial project scope, which called for hot fire testing at the end of detail. As the project scope changed to no longer including hot fire testing, it was decided that we would maintain these requirements to allow for more flexibility for future design teams. So with the hot fire test in mind, the test stand requirements were determined to be that it be able to handle at least the full thrust of our engine, as well as be able to maintain its strength and ductility at cryogenic temperatures due to its exposure to the cryogenic fuels. As well, we wanted it to be portable due to the unknown location of testing, as well as be corrosion resistant and be able to be fabricated on campus for a reasonable cost. The images behind me show the initial test stand design. It was designed to be able to be mounted in both a horizontal and vertical position to allow flexibility in testing, as well as having a large centrally mounted load plate for mounting of the engine. Analysis of the test stand was conducted in ANSYS. It was mounted in the horizontal position due to its non-symmetrical loading in this position. Also, it was a 2,500 pound load was applied to the load plate, and the mechanical properties used were that of 6061 T6 aluminum in its welded form. 6061 T6 aluminum is a heat-treated metal, and when welded, loses approximately 50% of its strength. Since the stand would be manufactured using welding, it was the lowest tensile strength was used. The initial analysis showed that there was a large amount of stress in the long unsupported beams supporting the mounting plate, and with significant stress concentrations at each end of those beams. Therefore, a revision was done to the test stand to add cross bracing halfway down the beams. A 1/2-inch square tube was used for this cross bracing. This stiffened the structure and reduced the deformation on the load mounting plate. The ANSYS analysis of this showed that the stress was significantly reduced and deformation was reduced to approximately 6/1000 of an inch at a 2,500 pound load. The stress concentrations were also significantly reduced, and the lowest factor of safety of the entire stand was approximately 6. The 6061 T6 aluminum was selected over steel due to its low weight, high corrosion resistance, low cost, and low cost. The material is planned to be ordered from Prescott Steel, as it is readily available there. The total cost of the entire stand is approximately $160, including all of the welding materials needed. The main structural supports would be 3/4 inch square tube with a 1/16 inch wall thickness, and the supporting struts would be the cross bracing is a 1/2 inch square tube, also with a 16th inch wall thickness. All of the load plates, including the main load mounting plate and the plates, the horizontal and vertical mounting plates, would be 1/2 inch and all material would be 6061 T6. As discussed earlier, welding significantly reduces the ultimate tensile strength of the material. Shown in the diagram on the right is how much the tensile strength is reduced in regards to distance from the weld. As you can see, the strength at the weld remains fairly stable. However, approximately a quarter inch from the weld, there is a significant reduction, and with a T6 heat treatment, the reduction is approximately 50%. Some of that strength can be recovered by performing an aging process post-weld. This process for 6061 T6 is a heating of 400 degrees for approximately an hour. Due to the small size of the test stand, it will fit in the composites oven, and the oven will handle that. So we're planning on placing the entire stand in the oven and doing the post-weld aging after construction. Now, head on to Jenna Humble.
Thank you, Eric. Again, my name is Jenna Humble, and I will be finishing up our presentation with our conclusions and recommendations. In summary, these are the original requirements we presented. We have not addressed the pump fed requirement as it is out of our scope. We also believe that we have met all of our requirements except for the throttling requirement, as mentioned earlier. We believe that we can get down to 45% of our max throttling, potentially lower, but that would be dependent on testing and the feed system. We recommend having a 3-phase detailed design semester. The first phase would be manufacturing. We are recommending the manufacturing of the ground test engine injector assembly, as well as the igniter, a cooling test section, and the test stand itself. The second phase would be a modeling phase, where we would complete a computational fluid dynamics model of our manifolding to get our velocity and pressure distributions at each of the injector ports. We would also be completing our structural and thermal models of the full thrust chamber assembly. Our testing phase would consist of a spray pattern test, which would test the injectors, and an injector pressure drop test, which would validate our model for our injector characteristics. We would also like to hot fire our igniter by the end of detailed design to validate that design, and we would like to complete a heat transfer test to validate our heat transfer model for the regenerative cooling system. This is our proposed budget. We have decided to use approximately $3,000 of the $5,000 budget. The majority of this goes into the manufacturing of our injector assembly, as the oxidizer dome and fuel ring manifold are not able to be fabricated on campus and will have to be outsourced. These are our work statistics for the semester. We are at 115% of our projected hours, and most of that was spent in engineering and documentation efforts, with a small portion for my project management. At this time, we would like to thank Eric Heiniger of Pyramid Space, our sponsor, as well as Dr. Brenda Haven and Dr. Matthew Haslam, our professors who guided us throughout the semester. We would also like to thank Dr. Michael Fabian and Dr. Shigeya Hayashibara, as well as Mr. Patrick David, for their technical support throughout this semester. At this time, are there any questions?
So my first question, as far as the ending, are you doing a hot fire test or not? Because I thought I heard both.
Not of the full engine. We're doing a hot fire test of the igniter, but the full engine will not be ready at that point.
Okay. And then so to that end, are you getting the feed systems from Pyramid, or?
We are not. We will have to source that ourselves.
Okay. And then my main concern in that is to make sure that with that everything, communicate with them and make sure that nothing freezes. Because I know freezing is bad.
We have kept that in mind, and it's definitely a concern for us.
Okay, keep that in mind. Also, just out of curiosity, do you know why natural gas? I just haven't really heard too much of natural gas. Is that a shifting trend, or?
It is a shifting trend. Natural gas has actually been proven to be quite an effective fuel, and it is readily available. It's currently being used by companies such as SpaceX and Blue Origin for their new engines.
If you go to slide 12, I think I might have just missed it or something, but interface downstream,
Yeah, so with the interfacing with the full nozzle attachments that would be attached to this truncated nozzle for a variety of applications. What does that say you're attached to?
Okay. Oh, for slide 20, there, I thought it might have been useful to just have like a little bit of an image for the two differences, just to be able to get a better understanding of that. And then for slide 25, it just looked like a lot of surface area. I just wanted to make sure you have, I mean, as far as having enough fuel to be able to support that much surface area that you're flowing, your flow rates are good enough for that.
Yes, we have checked that with our analysis, and we do have a sufficient flow rate.
And it's actually, I hadn't seen that style. For slide 32, just another sort of a visual sort of thing. The green, you got the whole other half of it, and it's all kind of clumped together. You may want to consider spreading that out a little bit to make it easier to read. All good. Oh, good comments 42. I really liked that, and I liked how it progressed. It was very awesome. Yeah, that was good stuff.
That doesn't reach much from that.
And then on 45, how come it's only a half? The oxidizer is only coming. It's a half circle, and it's not full. Was there a reason for not being full round?
It wasn't required to be full round. There were only 2 injector ports, one at each end of that semicircle. It helps with consistency in the flow pattern.
Okay. As far as calculating the 2,500 pounds, I think that was close to slide 52 over there. How did you get the 50 or the 2,500 pounds for the load?
So we had estimated, we have a requirement of 2,200 pounds. So we upped that for our requirements to 2,300 pounds in case of error within the engine itself. In addition, we will have the weight of the engine and any gimbals that may be designed in the future. So we wanted to have a factor of safety on our thrust requirement.
How about the maximum was 2,200?
Yes, our max thrust should be 2,200.
Was there any chance that it could do something crazy and get more?
We hope not, but it is a possibility, yes.
Okay.
Our hybrid guys went from 900 to 1,300 and a half a second.
Oh, jeez. Just out of curiosity, 56, where did that graph come from?
That was from Hobart's welding guide. It was they're a welding manufacturer.
And 58, more positive things. I like the check marks. I like that very clean, organized, good stuff. And I think that's it. Yeah.
Yeah. On the regenerative cooling analysis, did you do that by hand or did you do it with kind of software?
Initially, I used the NASA Special Pub 125 as well as RPA theory for rock repulsion analysis that was published, and did it inside an Excel file after analyzing the equations. It uses a Boltzmann theory approximation for heat transfer.
So you're saying marching forward, you're not talking transit conditions, you're saying physically marching
Yeah,
forward.
physically. Yeah.
Okay. Did you account for the supports in there and kind of flow deviation from that?
So far we have not accounted for that. That'll be within our fluid model and detailed design.
Okay.
But it shouldn't impede the flow too much.
No, it just could create some difference in the heat transfer with some mixing, and it is enough of the flow area, so I think that would be something worth looking into. That might be more of a CFD type model. That's all I have.
Are you running the igniter the whole time? I thought that's what, is that the plan? You're running it, so you're leaving it on all the time, or are you lighting and then turning it off?
We have the option. The options that are present. So
Which way are you
at this
leaning?
point, we are leaning towards running it.
And what's your biggest concern in this design? It's very complex.
The biggest concern for me is honestly sealing, because we're working both with cryogenic fluids and with combustion gases over 6,000 degrees Rankine. I'm worried about having our sealing remain intact.
Are you doing thermal stress analysis on your pedestals and all that stuff later? Is that, okay.
Yeah, that's part of the thermal models to be done in detail.
Overall, very, very clean.
One of your design criteria was reusability, and when your dual wall nozzle, your hot wall is going to be considerably, or your inner wall is going to be considerably hotter than the outer wall. And those struts are going to get there's going to be a different thermal growth. Those struts are going to get stressed. Are you planning on having the struts brazed, or having a geometry that gives them some compliance, or how are you going to handle the thermal fiber?
We were planning on having them brazed. We have not actually addressed that problem. So that would be something we can look more in depth in detail design.
Because until you do handle that problem, you can't really have that reusability check green. Was a temperature analysis done on the hot wall and cold wall? What were those temperatures?
So, using rock repulsion analysis, a software developed in Germany, we were able to input the geometry of our rocket engine, and from that it gave us temperatures throughout the engine. It's approximately, I believe, 6,700 degrees Rankine inside the initial combustion chamber, and at the throat it's somewhere around 6,500 degrees Rankine, and the nozzles are 6,300 degrees Rankine.
What are the material temperatures in your nozzle, hot wall and cold wall?
Material temperatures were estimated to be about 4,900 Rankine, I believe, for the nozzle. That was before you apply the cryogenic flow to the chamber wall.
So you haven't done a thermal analysis with the cryo flow?
Oh no, it was done with the cryo flow.
So 4,900 degrees?
Well, the approximation that was used in the NASA special pump was taking the hot gas temperature of the inside of the chamber, taking into effect then boundary layer cooling, and then on the other side of that you have the cryogenic flow and the approximate temperature of the wall. I did the entire calculation in terms of heat flux, so I never took the temperature, but material survivability was taken into consideration. So.
Okay. I was just wondering how well you were staying within the material capabilities of the AIMS 214.
Yes. It should survive. I don't remember the exact temperature of the material at the nozzle off the top of my head, but based on my analysis, the material should survive.
On the liquid, or the natural gas, was there any literature data in terms of whether there's a coking sensitivity in terms of metal temperature?
Yes, there have been difficulties shown with liquid natural gas as it is still a hydrocarbon. However, in our research into AIMS 214, it is highly resistant to coking itself, so that will reduce the risk of having coking in the injector ports.
What is the temperature where you would potentially risk the onset of coking?
I'm not sure. I can look it up.
Would probably, if possible, like to keep your wall temperatures below that.
Yes.
If you do get coking, it'll give you a very painful day.
Yes. The NASA Special Pub actually has engines that were designed for coking. They use coking as an added thermal barrier to reduce the wall temperature as well. So it is not necessarily detrimental in the combustion chamber if it is limited. We're only very concerned about it in the injector ports themselves.
You're not concerned about it at all in the cryo cooling chambers if you get a hot spot in your wall?
We're not worried about that yet. I will be doing an analysis on the manifolding in detail design when we're looking at temperature distributions, and if we do have a hot spike in there, yes, we won't be concerned about it.
Okay.
Okay, overall, it's pretty good. Just a few, I guess, concerns. First off, slide 6. Just for consistency's sake, I'd say throw that in a matrix, just like at your conclusion, so that way we're all trained to see, okay, this is what we're going to see later. Just a quick consistency thing. Also, not to call you out on this, but just a quick thing of things you should say. Saying words like should is a little concerning. Yes or no is a little preferable. I'm just saying that because someone might ask one is there isn't. So just be careful the way you say it. Go to slide 23, please. So your chamber shell is a 16-inch, right?
Yes.
Will the regenerative cooling allow it to survive if it's that thin?
Yes.
Okay.
The regenerative cooling analysis that was performed, the actual required thickness of the wall was much less than that, just due to general availability of products. We wanted to go with a pretty standardized size, as well as have a, it needed to be thick enough that we had some factor of safety, but also thin enough that you could still actually have the cooling flow through the tail.
Okay. It just seems awfully thin, so I'm worried about if there's any defect on hospital failure. For slide 25, this is kind of a dumb question, I just don't understand. So how are you pumping it in and then out? Because you're pumping, let's see, oxide, pumping the LNG, which is fuel, right?
Yeah.
So how are you pumping it in and then how's it coming out again? Sorry.
Yeah, so the fuel will enter through a manifold that Marcus talked about before my slides. This is the manifold here. The manifold will then pass underneath this channel created with a nozzle attachment plate, a lower fuel manifold ring into the into the cooling system itself.
Okay. Sorry, I was just a little confused about that. Slide 36. You guys have talked to Patrick Dave about this, right?
Correct.
Good. Okay. So I just wanted to make sure, like, he said it is simplified, right? Not
Yes.
you were saying it's simplified.
Yes, no, we've talked with Patrick about the manufacturing for all of
Okay,
this.
good. Because I've run into that too. You say it's simplified, you take the machinist, and he's like, no, it's not. Once again, on the 42, that's good animation. A quick question too about your igniter. How big is it? I have no idea what the size of it is.
Okay, so the length of the igniter is just under 3 inches.
Okay.
The inner chamber diameter is about 3/8 of an inch.
Okay. Okay. Because I was just sitting here wondering, well, how big is it?
Yes.
Because you're talking about modular parts and thinking, well, do you want to just drop in a whole new igniter? Or why replace parts? But okay, it's big enough to figure that, I guess.
Yes, and the outer diameter was designed to be 1.5 inches, purely to help with the clamping down on the plates as well as having a little extra material there. And that it can all essentially be machined from your own stock.
Okay. Yeah, just wanted to know. I had a question about 59. Maybe answer this before I was paying attention. Why is modeling after manufacturing? Do you need your assembled model or the assembled asset like that?
We don't need the assembled model for the modeling. However, these are going to be very long lead time parts, so we wanted to do all of the work to get the manufacturing done first, so we have as long as needed to get this manufactured.
Okay, just make sure you make that good.
Yes.
I'm not used to seeing that order. That was kind of concerning. That's an expensive way to operate where you build the thing, then model it.
Ideally, we would like to model it first, but given our time constraints, that's not feasible.
Okay.
Would it make sense to have preliminary modeling ahead of manufacturing so that you have some documentation in terms of why you're making what you're making?
Yes, we are working on some preliminary modeling at this point. It's just not to a point where we can present the results.
Okay. Again, that caused me some heartburn as well. Having a modeling step so that you know why you're manufacturing things in a specific shape always gives your customers a better feeling.
Yes.
Customers got to be happy. I guess one just quick question on values for slide 60, or I guess you could also go to slide 54. Sorry, it's 63. costs you said you applied, factors in before the loan applied to the model?
So for the test stand,
Yes.
so we have a thrust of 2,200 pounds. We upped that by 100 pounds just in case of fluctuations during testing. And then because we're going to have both our engine and possibly a gimbal mounted to this, we added an extra 200 pounds to the safety because we would have a bending moment.
Okay. Just seems a little close. I know you're just starting the United, but full scale it seems a little close. You're civil engineering at this point. You make it really happy.
Yeah, we believe that it can go above that. As Eric mentioned earlier, our minimum factor of safety is around 6. So we do have capability to do that.
Okay. That's all I got. Otherwise, pretty good. Very clean. Dr. Fabian said.
Thank you. Questions?
I think in general, slide number is bigger.
Yes.
So, Jen, I heard you say that you chose 6061 because you do not plan on hot firing,
Correct.
but in the future, isn't hot fire
Yes.
the plan? So, will you have to remanufacture these parts because of the temperature differential?
We will only have to remanufacture the injector plate itself, as that is the only one made out of a different material. That's the Haynes 214.
Right. But, so for your prototype, that will also be 6061?
Yes.
So the remaining 6061 will not see high temperature?
No, it will only be at cryogenic temperatures.
And then I had the same comment. Modeling before manufacturing does not make sense. I'm sorry. You have to have something that you are using to give your customer warm and fuzzy, at least, that you are manufacturing something. So what is your plan, since you're not going to be able to do modeling until after manufacturing? What's your plan if you are you not able to get the flow rates that you?
We are working on the modeling currently. As I mentioned earlier, we just don't have it to the point where we are certain about our values enough to present it to a panel. We will be working on that over Christmas break, and we will have that at least preliminary numbers by the time we send all of our components off for manufacturing.
But do you have a plan for when you do the full modeling using CFD or whatever you plan on using? What happens if you do not get the flow that you need in terms of changing your existing structure?
The main part that would restrict the flow would be the passage plate itself. And because of our modular design, we would be able to remove the passage plate from our assembly without remanufacturing everything else. So we would be able to remanufacture that specific part and put it back into our assembly for testing.
Somehow, if you could convey that message that the components are all modeled before manufacturing, and then the supplemental modeling would be done if the system check indicated that there was a need